Good morning, children. Now we have our judges with you. He's a loving person. All of you know he's Amitabh sir, and we have Reshmi with us. Okay, so we would start our presentation, and after the presentation, sir will inspire us to move forward. Okay, he's a loving person. Most of you know we have to learn from him. We have to go forward with his inspiration. Um, Sir, can you hear us? Reshmi, I think there's a microphone option. Reshmi, we can't hear you. Sir, we cannot hear you.
Yes, ma'am.
Okay, okay. So, sir, we are starting. We are starting.
Okay, okay, ma'am.
Okay. So,
Okay, ma'am.
Arunangshu with your team.
Good morning, our respected judges and my dear friends. Team VGO is going to share their presentation. Upthrust.
Okay, so you
Uh, Arunangshu, the first slide. Don't be nervous. Don't be nervous. You all know, sir. Sir is not strict. So don't be nervous. It's the first time he knows, and he knows that you all are doing from different houses. You all didn't even meet together. So we all appreciate your effort. Don't be nervous. Start from the first floor. First
Yes,
slide.
ma'am. Yes, ma'am.
First slide.
Upthrust and buoyancy. Presented by Team VGO.
It's coming late because of the animations. Next time when you do, children, try to avoid too much of animations. It takes time to come. No problem. Try. We are waiting. Try.
And can you see the next slide?
It will take time because you have given animations. Can you just scroll,
Ma'am,
Arunaksh?
ma'am, what is the screen that you can see now?
Nothing is nothing we can see. We can see the blue slide, blue screen, and a red strip at the end. Can you just yes, it was coming. It was coming.
Ma'am, now?
It's because of the animations, no? Um, Arunakshu, can you all scroll without the animations?
Okay, ma'am. Okay, ma'am. I'm trying to do that.
Just scroll without the animations.
Ma'am, can you see the screen?
I can see the blue screen, nothing else. Your blue slide, because the animations take time to come. Just scroll and try to present your con. Do one thing, Arunakshu. I'm giving you all time. Let us go to the next team. Okay, by this time, you all try to make a PDF or something without the animations, just try to display. Okay, okay, we are going to the next team, Arunakshu. Try to do something without the animations if you can present. Okay, we'll come to your team last. So we go to the next team. After Upthrust, next team, get ready. Don't be tense. Don't be tensed. It's the first time we all know, and you all know, sir is not like that. Don't be tensed. Just relax. Second team, can you just raise your hand so that I can make you a presenter? First off, please see that your members are made a presenter.
Ma'am, please wait 1 minute. We are reading ourselves.
Yes. So get ready. Who is presenting? Can you please share your screen?
No, Kaustav is presenting, but he is taking some time to set up his computer. So, ma'am, please give us 1 minute.
Okay. Third team, be ready, okay?
Yes, ma'am.
Ma'am, is my screen visible?
Yes, yes. Your screen is visible. Start your presentation.
Okay.
Please minimize the sliders.
Apparent weight. The weight of an object is the force of gravity on the object. Weight is the force that makes most ordinary objects fall into the ground. Near the surface of the earth, weight is directed towards the center of the earth, that is downward, and its magnitude is ma, where m is the mass of the object and a is the acceleration due to gravity, about 9.80 meter per second square.
Suppose a box of mass 5.0 kg is resting on the floor. Gravity is applying a force of 5.0 into 9.80 is equals to 49 Newton on the box. Usually, forces produce accelerations, but the floor is applying an upward force on the box of exactly 49 Newton. This offsets the force of gravity and hence no acceleration.
In this simple example, the weight of the box, 49 Newton, has the same magnitude as the normal force of the floor on the box.
Next, suppose that the box is on the floor of an elevator and that the elevator is accelerating upward 3.0 meter per second square. The floor is now applying two forces on the box, one to cancel the effect of gravity and the other to accelerate the box 3.0 meter per second square.
The total normal force of the floor on the box is Fm is equals to Ma is equals to 5.0 into 9.80 plus 3.0 is equals to 64 Newton.
So even though the weight of the box is only 49 Newton, it is experiencing the same force as a box of weight 64 Newton. Therefore, we say that 64 Newton is the apparent weight of the box.
In physics, apparent weight is a property of object that corresponds to how heavy an object is. The apparent weight of an object will differ from the weight of an object whenever the force of gravity acting on the object is not balanced by an equal but opposite normal force.
By definition, we can define apparent weight as the weight of an object is equal to the magnitude of the force of gravity acting on it. This means that even a weightless astronaut is in low Earth orbit with an apparent weight of 0 has almost the same weight as he would have while standing on the ground. This is due to the force of gravity in low Earth orbit and on the ground being almost the same. We can define apparent weight in other terms also. That when an object is held still underwater, it appears to weigh less than it does in air because the buoyant force is helping to hold it up as it balances its weight while it is in water. For this reason, the reduced force you need to apply to hold the object is known as the apparent weight.
An object that rests on the ground is subject to a normal force exerted by the ground. The normal force acts only on the boundary of the object that is in contact with the ground. This force is transferred into the body. The force of gravity on every part of the body is balanced by stress forces acting on that part.
A weightless astronaut feels weightless due to the absence of these stress forces. By defining the apparent weight of an object in terms of normal forces, one can capture this effect of the stress forces. A common definition is the force the body exerts on whatever it rests on.
The apparent weight can also differ from weight when an object is partially or completely immersed in a fluid, where there is an upthrust from the liquid that is working against the force of gravity.
Another example is the weight of an object or person riding in an elevator. When the elevator begins rising, the object begins exerting a force in the downward direction. If a scale was used, it would be seen that the weight of the object is becoming heavier because of the downward force, changing the apparent weight.
The role of apparent weight is also important in fluidization when dealing with a number of particles, as it is the amount of force that the upward drag force needs to overcome in order for the particles to rise and for fluidization to occur.
An object's apparent weight is equal to its actual weight except if the object has an acceleration with a vertical component relative to the earth, as in a lift, a rocket, or a roller coaster. The formula is W equals to mg minus ma. Some force other than the Earth's gravity and the normal force is acting on the object. This may be buoyancy, magnetic force, centrifugal force, or the gravitational force of another body. The formula is Wa equals to mg minus F.
Apparent weight and weightlessness. Astronauts who were orbiting the Earth experienced a sensation of weightlessness. This is similar to the sensation you experience on a giant wheel or a roller coaster. To understand what causes weightlessness, an idea about true weight and apparent weight is necessary. True weight and apparent weight, or true weight of a body, is equal to the force exerted by the earth on it. The true weight of a body of mass m is given by the relation W is equal to mg. The weight of a body is measured with the help of a weighing machine or by a spring balance. When a body is kept on the platform of a weighing machine, its weight is given by the normal contact force between the body and the platform of the machine. Similarly, when a body is suspended from a spring balance, its weight is given by the normal contact force between the spring and the body. When the body is placed on a weighing machine, the forces acting on the body are the force of gravity on its weighing machine, W. acting downwards the upward normal contact force and exerted by the platform of the machine. It is this upward normal contact force exerted by any supporting surface which gives a feeling of weight. This upward normal contact force is called the apparent weight of the body. The value of this upward normal contact force and depends upon the state of motion of the body. To understand the concept of apparent weight, let us imagine a person standing on a weighing machine placed on the floor of an elevator. Now observe the position of the pointer of the weighing machine, which the elevator is at rest when the elevator moves down with a constant acceleration. When the elevator moves upwards with a constant acceleration and when the elevator falls freely, we observe that the apparent weight registered by the machine is equal to the true weight of the body, less than the true weight of the body, more than the true weight of the body, and equal to 0.
The apparent weight of a body depends upon the state of motion of the body. When the elevator is at rest, the person inside it is also at rest. External force is equals to 0. Therefore, the true weight of the person is W acts in vertically downwards is equals to the normal force in acting vertically upwards. In this case, the weighing machine registers the true weight of the body. When the elevator moves down with a constant acceleration, a net force acting on a person is equals to true weight of the person minus normal contact force. N is less than the mg of the person, thus the scale reads less than the true weight of the person. When the elevator moves upwards with an acceleration a, net force acting on a person is equal to true weight of the person minus normal contact force. N is greater than the true weight of the body. Therefore, the scale reads more than the true weight of the body. When the elevator falls freely, that is, if its cable break, then both the person and the weighing machine falls with the same direction. Mg is equals to mg minus n, or n is equals to mg minus mg, that is equals to 0. Thus the apparent weight of freely falling of a person or a body is 0, that is, the person or body appear weightless when falling freely or through the influence of gravity. At this stage, weighing machine moves to 0. Hence we see that during the state of weightlessness, the force of attraction due to gravity does not become 0. It is the average weight of the body which becomes 0 due to the weightlessness. Weightlessness in space. The spaceship and the astronaut orbiting in the Earth has a certain height actually in a continuity of free fall towards the Earth. As a result, the astronaut does not exert any force on the floor of the side spaceship, and the side and the floor of the spaceship do not push the person up. The astronaut therefore experiences weightlessness while orbiting around the Earth.
In physics, apparent weight is a property of objects that corresponds to how heavy an object is. The apparent weight of an object will differ from the weight of an object whenever the force of gravity acting on the object is not balanced by an equal but opposite normal force. Our weight is the magnitude of the force of gravity acting on us, which at the Earth's surface is equivalent to our mass in kilograms into 9.8 Newton per kg. Our apparent weight is this true weight and also the effect of some other acceleration or force that affects us.
Very, very good collection, children. You have done your best within this short time. I don't know how you have done it. I don't think you need my lecture anymore. You know the topic more than me. You have done enough research and very, very good presentation. I'm telling you, a very Good presentation, and I would like to show your presentation to my children also, because I won't be able to collect so much of information and give it to the children. Very good, very good.
Thank you,
Now we
ma'am.
go to the next team,
Thank you,
children.
ma'am.
Put your
Thank
hands
you, ma'am.
down. Put your hands down. Move to the third team. Uh, Team 3, the third team. Arunangshu, by the way, get ready. Before you will be displaying your fifth.
Yes, ma'am. We are ready. Can you?
Okay, fifth. Okay, first we are going to show. Okay. Then are you all ready, Arunangshu?
Yes,
Are you
ma'am. We have removed the animations.
okay? So we'll do one thing, children. First, let Arunangshu prepare, show us, because it goes serially. First, we go to upthrust, then apparent weight we have seen. Due to upthrust, the apparent weight changes. Then we'll move on to Archimedes principle. After Archimedes, we'll move to relative density, flotation, and then we are going to wind up the chapter. So, Pratiti, so Arunangshu's team, can you just put your hands up? Arunangshu's team,
Ma'am, Arjun is going to present from our team.
okay. So, so Arunangshu, your team is going to present the topic upthrust. So
Yes, ma'am.
we are going to learn what is upthrust from your team.
Upthrust and buoyancy, presented by Team Vibgyor. Yes, ma'am. Repeating once more. Upthrust and buoyancy, presented by Team Vibgyor.
Good morning, everyone. So today I'm going to explain you all about the meaning of two terms. Number one is upthrust and number two is buoyancy. So what is upthrust? The upward force that is experienced by a body when it is partly or completely immersed in a fluid is called upthrust. Another term that is used for upthrust is buoyant force. So we can say that the upward force exerted on a body by the fluid in which it is submerged is called upthrust. And what is buoyancy? The property of a liquid to exert upward force on a body immersed in it is called buoyancy. It is denoted by the symbol Fb. We will learn about this property in the upcoming slides. In this slide, you can see there is a diagrammatic representation of buoyancy. Here, a column of water is shown in which an object is partially immersed. Here are a few terms. The term rho fluid symbolizes the density of the liquid, and the term rho object symbolizes density of the liquid. The term m object is used to represent the mass of the object, and there is also an arrow which shows that the force of gravity is acting normally or perpendicularly on the object. And if you observe closely, there is also an arrow present in the water area which is showing that buoyancy is acting opposite in an opposite direction to that of gravity.
What is flotation? When a solid is floating in a fluid, the weight of whole solid acting vertically downwards at its center of gravity is equal to the weight of fluid displaced by immersed part of solid acting vertically upward at its center of buoyancy. Following are the points to remember in flotation. Number 1, the displaced volume of fluid is equal to the volume of the object which is immersed in the fluid. Number 2, if the weight of the object is greater than the upthrust, then the object will sink in the fluid. And number 3, if the weight of the object is equal to the upthrust, then the object is balanced, making the object float. Now, what is sinking? If the upthrust is less than the weight of the object will sink. If the density of the object is greater than the density of the fluid, the object can never displace enough fluid to create an upthrust that will hold its weight up, so it sinks. Experiments on buoyancy. Experiment 1. Push an empty can into water. For this experiment, we need to take an empty can. We first need to close its mouth with an airtight stopper tightly and ensure that no water seeps into it. Next, we need to put it in a tub filled with water. We see that it floats with a large portion of it above the water surface. If we push the bottle or the can into water, we feel an upward force which opposes the push, and we find it increasingly difficult to push the can further into the water. It is also noticed that as the can is pushed more and more inside the water, more and more force is required to push it further to completely immerse it in water. Now, experiment 2. Pushing a cork into water. If a piece of cork is placed on the surface of water in a tub, we see that it floats with nearly 2/5 of its volume inside the water. If the cork is pushed into the water and then released, we see that it again comes to the surface and floats. If the cork is kept immersed, our fingers will experience an upward force. The behavior of the cork is similar to the empty can or the bottle.
Characteristics of upthrust. Upthrust has the following main characteristics. Number 1, larger the volume of the body submerged in fluid, greater is upthrust. More the density of the fluid, greater is upthrust. And number 3, upthrust acts on the body in the upward direction at the center of gravity of the displaced fluid, which is also called the center of buoyancy. Reasons for upthrust. We know that a liquid contained in a vessel exerts pressure at all points and in all directions. When a body, say a block of area of cross-section A, is immersed in a liquid, the pressure P2 acting upwards on the lower face of the block, which is at a greater depth in comparison to the upper face of the block, is more than the pressure P1 exerted downwards on the upper face of the block, which is at a lesser depth in comparison to the downward face of the block. Since force is equal to pressure into area, the difference in pressure due to the liquid on the two faces of the block causes a net upward force, that is upthrust, is equal to P2 minus P1 A on the body. However, the thrust F on the side walls of the body get neutralized as they are equal in magnitude and opposite in directions. Note, if a lamina, a thin sheet, is immersed in liquid, the pressure on both surfaces will be nearly same, so the liquid will exert negligible upthrust on it, causing it to sink into the liquid due to its own weight.
That we have seen what is upthrust, what are the characteristics and reasons for upthrust, let us see what is the formula for calculating upthrust. Refer to the diagram given alongside. Let an object be immersed in a fluid of density rho. Let acceleration due to gravity be small g, which is roughly equal to 9.8 meter per second square. Downward thrust on the upper side of the object is represented by F1. Upward thrust on the downward side of the object is represented by F2. Cross-sectional area of both the sides, that is upper and lower sides of the object, is represented by capital A. H1 denotes the distance between the surface of the fluid and the upper surface of the object, and the distance between the surface of the fluid and the lower side of the object is denoted by H1. So, what will be the pressure on the upper surface of the object at depth H1? At depth H1, the pressure on the upper surface of the object will be equals to H1 into rho into G. Now we know that pressure equals to thrust by area, or we can also say that thrust equals to pressure into area. Therefore, downward thrust on the upper surface of the object will be pressure into area, that will be equals to H1 rho G capital A. This is our equation number 1. At depth H2, pressure on the downward surface of the object will be equals to H2 rho G. Therefore, upward thrust on the lower surface of the body will be H2 rho G capital A. This is our equation number 2. The horizontal thrust at various points of the vertical side of the object get balanced. Why? Because liquid pressure is same at all points at the same depth in a given liquid. From the above equations 1 and 2, it is clear that F2 is greater than F1. Since H2 is greater than H1, and therefore the body will experience a net upward force. So the question arises, how can we calculate that net upward force? We can calculate that net upward force by subtracting F1 from F2. That will be equals to H2 rho Ga minus H1 rho Ga. Taking common, we get capital A into H2 minus H1 into rho G. But we know that A into H2 minus H1 is equals to V, which represents the volume of the body when it is submerged in the fluid. And therefore, upthrust FB will be equals to V into rho into G. We know that upthrust is a force. And since it is a force, it is measured in terms of Newton and kilogram force, that is kgf.
Respected judges, before ending our presentation, let us do a quick recapitulation of what we have done till now about upthrust or buoyancy. Number 1, upthrust is a non-contact force. Number 2, a body floats in a liquid if its density is less than the density of the liquid. The body will sink if its density is more than the density of the liquid, and the body will remain suspended if its density is equal to the density of the liquid. And the last, effects of upthrust. The effect of upthrust, as we know, is that the weight of the body immersed in a liquid appears to be less than its actual weight. Larger the volume of the body, some greater is the upthrust. More the density of the body, more is the upthrust.
Excellent, children. Excellent. I don't know whether you'll need my teaching anymore on this chapter. You've explained upthrust more than what will I teach next day? You already know that upthrust is V rho G. You already know. So what am I going to teach you? You know more than me. Very good. Very good presentation. And I'm going to give you recordings in the group so you can go through it again and again, everyone. So you'll be ready with the chapter. So put your hands down. Let us move to team number 3. Put your hands down, children. Put your hands down. Now, next we move on to Archimedes principle. What is Archimedes principle? Next team, please raise your hand so that I can make you a presenter. After Archimedes principle, we'll move to relative density. So relative density team, get prepared after this. So now we are going to learn what is Archimedes principle. First, we knew what is upthrust. We came to know what is apparent weight. And now we are going to move to Archimedes principle. What Archimedes said. So Anshuman, your team is ready. Start
Yes.
sharing the screen. Minimize the size. And the type is
Good morning to respected ma'am and judges and all my dear friends. Today Team Energy has prepared a brief presentation on Archimedes principle. Archimedes principle is a law of physics fundamental to fluid mechanics which was formulated by Greek mathematician and physicist Archimedes of Syracuse. Now we shall move on to the definition of Archimedes principle.
If you have given animations, you can just scroll. If it's not coming, no problem. No problem. So next time when you go to your colleges or higher education, try to give as much, minimize your animations. It takes time, okay? If it's not coming, Koshiki, you can just scroll, no problem. Don't be tensed. Don't be tensed. Do you all need time? Koshiki, do you all need time?
No, ma'am, just a minute.
Okay, just scroll. If it's not coming, just scroll. Because we are learning the subject, not the animations.
Is it
Yes.
showing now?
Yes, it's coming. Just minimize that one, the site icon.
Ma'am, if I minimize now, then I won't be able to mute myself after reading this.
Okay, okay, it's up to you. Up to you.
Definition of Archimedes principle. Let us know what the Archimedes principle states. Archimedes principle states that an object immersed in a fluid experiences a buoyant force that is equal in magnitude to the force of gravity on the displaced fluid. Now let's study Archimedes principle using an example. Archimedes principle states that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces and acts in the upward direction at the center of the mass of the displaced fluid. Example, when you forcibly try to put a ball or any object in a bucket full of water. The below picture describes Archimedes' principle where Fb is the force exerted by the fluid or the upthrust and Wb is the weight of the body. Moving on to the next slide. So now we will start with the applications on Archimedes principle. The first application we will do is submarines stay underwater. Submarines are made up of a ballast tank which contains water. This maintains the weight of the submarine, which becomes more than the buoyant force, so it can stay underwater. And when water is released from the ballast tank, it floats. Thus, this is how submarines stay underwater. Now we will move on to the next application, that is hot air balloon rises and floats in midair. Hot air balloon rises and floats in the midair as the buoyant force is more than its weight, and it floats, and when the buoyant force of the hot air balloon it's more, it starts descending. So this is and it is stationary if the weight of the if its weight is equal to its buoyant force. So the weight of the liquid, the weight of the hot air balloon can be maintained by varying the quantity of hot air in the balloon. And now we'll move on to the last application, that is hydrometer uses Archimedes principle. Hydrometer is a device used to determine relative density of liquids, and its operations are based on Archimedes' principle, which states that the object displaces its own weight within a liquid in which it floats. So now we'll move on to the next slide, which will show the first experiment to verify Archimedes' principle.
In this experiment, we are going to verify Archimedes' principle. We need a hollow cylinder marked as A and a solid cylinder marked as C and a physical balance marked as B, a beaker, some weights and water. Now to do this experiment, we have to suspend the two cylinders A and C from the left arm of the physical balance B such that cylinder C is below cylinder A. We have to balance the beam by keeping the weights on its right arm. Now we have to immerse cylinder C in beaker filled with water such that it does not touch the sides and bottom of the beaker. It is observed that, moving on to the observation, it is observed that the left arm of the physical balance rises up due to the loss in weight of cylinder C, which is due to the upthrust of water on cylinder C. If we pour water in cylinder A until it is completely filled, it is observed that the physical balance B is balanced again. Thus, it is clear that the weight of water in cylinder A is equal to the weight of water displaced by cylinder C since both have the same volume. Thus, the upthrust acting on cylinder C is equal to the weight of water displaced by it. Therefore, from this experiment, we can conclude that Archimedes' principle is verified. The picture of the above experiment is given below. Now, we shall move on to the next experiment to prove Archimedes' principle.
So in this experiment, again we will verify Archimedes' principle. To carry out this experiment, we need a solid body, a spring balance, an eureka can, and a measuring cylinder. Now we have to perform the experiment. For this, we had already placed the eureka can, and where the spout ends there is a measuring cylinder. Now we first measure the weight of the solid body in air using the spring balance. We need to note the reading for the verification. Then we again measure the weight of the solid body, but now we put it in the Eureka can that was filled with water but to the level of the spout. When the body is immersed in the water, some of the water falls out through the spout into the measuring cylinder. Now we note down the reading of the spring balance and the measuring cylinder. We will notice that the weight of the solid body in air is 250 gf, the weight of the solid body in water is 150 gf, and the volume of the water in the measuring cylinder is 100 mm, or we can say it as 100 cc. Moving on to the next slide, we can see various changes, or we can say various certain changes which are like the loss in the weight is equal to 250 gf minus 150 gf, that is the weight of the solid body in air minus the weight of the solid body in water. So we get that it is 100 gf. We can mark this as equation 1. We know that volume of the water displaced is equal to the volume of the solid. So the volume of the water displaced is 100 cc. Since the density of water is 1 gram per cc, the weight of the water displaced is 100 gf. We can mark it as equation 2. So as we compare equation 1 and 2, we get that the weight of the water displaced is equal to loss in the weight of the solid body, or we can say it as upthrust. From this experiment, we are able to verify Archimedes' principle, that is when a body is immersed partially or completely in a liquid, it experiences an upthrust which is equal to the weight of the liquid displaced. Now we are moving on to the next topic, that is the definition of flotation and sinking.
In order to know the flotation and sinking of solids of different densities, we need to know what is buoyant force. So it is the upward force exerted by any fluid on a body placed or immersed in the fluid. Here, three cases may occur. Case 1. When the weight of a body is greater than the upthrust, the body sinks in the liquid. The net force acts downwards. Case 2. When the weight of the body is exactly equal to the upthrust exerted by the liquid, the body floats on the surface with the net force acting on the body remaining zero. Case 3. When the body is weighing less than the upthrust, the body floats as the net force acts upwards. However, only that much volume of the body
will be submerged inside the liquid, due to which upthrust and the weight of the body gets balanced. Therefore, the net force is zero in this case too. From the above three cases, it can be inferred that a body with density more than the liquid sinks in that liquid, whereas the density of the body less than or equal to that of the liquid floats on the liquid. Here I conclude my speech, and now we shall move on to the next speaker.
In the following experiment, it will be proved that objects which have lower density than a particular liquid will float on it. On the other hand, objects which have density greater than that of the particular liquid will sink in it. For the experiment, we will need an iron nail and a cork, both having the same mass. We will also need a cup containing water. If we place the iron nail on the surface of water, the nail will sink as it has more density than water. This means that the upthrust of water on the nail pushing it upwards is less than the force of gravity pulling the nail downwards. As a result, the nail sinks. But when we place a cork on the surface of water, it will remain afloat. This means that the upthrust of water pushing the cork upwards is more than the upthrust of water acting on the nail. To conclude, I would say that this experiment proves that the objects having greater density than a liquid sink in it, and those with lesser density than a liquid float on it. After having said this, now we shall move on to the next slide of the PowerPoint.
In this experiment, I'm going to show you the flotation and sinking of bodies having different densities when placed on the surface of water. In case 1, we are dealing with flotation of body when placed on the surface of water. Here I will take a body which is having a density which is equal to density of water and place it on the surface of water. I will observe that the body is floating on the surface of water, as because the upthrust which is due to the submerged portion of the body becomes equal to total weight of the body. For this reason, the buoyant force which is acting vertically upward becomes equal to total weight of the body. Now we are moving on to the next slide. Our next slide is on the flotation of body with whole of its volume inside water. Here in this case, we are going to see that if the body is placed on the surface of water with a density equals to density of water, the body will float with whole of its volume inside water. Here we can conclude that if a body is placed on the surface of water with a density equal to density of water, the body will float with whole of its volume inside water. Now we move on to the next slide, which is the sinking of body in the water. In this case, we will take a body which is having a density more than the density of water and place it on the surface of water. We will observe that the body is sinking in the water, as because the density of the body is more than density of water. The upthrust which is acting vertically upward cannot tackle the force of the gravity, and the weight of the body acts vertically downward and gets attracted by the gravitational pull of the earth. For this reason, the body sinks downward in the water. Here I will conclude my point by saying a few lines. If the body having a density more than a density of water, the body will sinks in the water. If the density of the body is less than density of water, the body will float on the surface of water. Now I conclude my speech and I'm moving on to the next slide, which is the conclusion of Archimedes' principle.
So by this we end our presentation here. Thank you everyone for your cooperation.
So thank you, children, for telling us what Archimedes said. Can you just lower your hand, children? So we'll move on to the next team. We'll move a very nice presentation. I don't know how you all managed within this short time to prepare yourself. So next we move on to the fourth team. We are going to learn what is relative density. So Tamojoy, you are going to share your screen. I'm making your team the presenter. get ready. I'm making your team the presenter. After relative density, we are going to move to flotation. So, team number 5, get ready.
A very good morning to our honorable teacher, our judges, and our classmates. This is Team Rainbow, and today we are going to show you all a presentation on relative density. Hope you all will like it. Here we go.
What is density? To understand what relative density is, we need to know what density is all about. Let us begin with an example for better understanding. If we take equal volumes of wood and iron, we would notice that the mass of iron would be much more than the mass of equal volume of wood. This is because the particles of iron are much more closely packed than those in wood. In other words, we can say iron is denser than wood. Therefore, we can say that density is a term which is used to explain that equal volume of different substances can have different mass as well as same mass. To conclude with, we can say that density of a substance is its mass per unit volume. That is, the mass of the substance by the volume of that substance. It is a scalar quantity and is represented by rho or the letter D, and mass is represented by the letter m and volume is represented by the letter v. Therefore, the formula of density can be written as d is equal to m by v.
Unit of density. We all know that density equal to mass by volume, or rho is equal to m by v. Thus, density can be explained as the relationship between the mass of the substance and the volume it takes up. The SI unit of mass is kg and the SI unit of volume is meter cube. Therefore, SI unit of density is kg per meter cube and CGS unit of density is gram per centimeter cube. Though SI unit of density is kg per meter cube, for convenience, we use gram per centimeter cube for solids, gram per milliliter for liquids, and gram per liter for gases.
Relative density. We know that the density of water at 4 degrees Celsius is 1 gram per centimeter cube or 1000 kg per meter cube. Treating it as a standard, the density of a substance can be compared with the density of water at 4 degrees Celsius, and the ratio so obtained is termed as the relative density of that substance. Thus, the relative density of a substance is the ratio of the density of that substance to the density of water at 4 degrees Celsius. That is, relative density equals to density of substance divided by the density of water at 4 degrees Celsius, or the mass of unit volume of substance divided by the mass of unit volume of water at 4 degrees Celsius. Thus, the relative density of a substance can also be defined as the ratio of the mass of a certain volume of a substance to the mass of an equal volume of water at 4 degrees Celsius. And the relative density is a scalar quantity.
We all know that the SI unit of density is kg per meter cube. The relative density is defined as the ratio of the reference substance. When placed mathematically, the unit on both numerator and the denominator are found to be the same. Hence, cancels out and proves relative density to be a unitless property.
How does relative density determine the floating and sinking of bodies? In the picture shown, we can see three bodies with different densities put in water. In the first case, the density of the body is greater than that of water. Therefore, the body sinks. Now, we know that relative density of a substance is the ratio of the density of the substance to that of the water at 4 degrees centigrade. Here, the ratio of their densities is greater than 1. Therefore, we can conclude that when relative density is greater than 1, the body will sink down. In the second case, the density of the body is equal to that of water. So, the body floats just below the surface of water. Here, the ratio of the densities is equal to 1. Therefore, we can conclude that when relative density equal to 1, the body will float just below the surface of the liquid. And in the third case, the density of the body is less than that of water. So the body is partially submerged inside water. Here, the ratio of the densities is less than 1. Therefore, we can conclude that when relative density is less than 1, the body will be partially submerged inside water.
What is the relationship between density and relative density? While calculating the relative density of a substance from its density or density from its relative density, we note that in the CGS system, density of water at 4 degrees Celsius is 1 gram per centimeter cube. Relative density or RD of the substance is equal to the numerical value of density of that substance. Thus, RD is equal to the density of the substance in gram per centimeter cube by 1 gram per centimeter cube, or RD is equal to numerical value of the density. In SI system, density of water at 4 degrees Celsius is 1000 kg per meter cube. The relative density or RD is equal to density of the substance in kg per meter cube by 1000 kg per meter cube, or RD is equal to the numerical value of density into 10 to the power minus 3. For example, the density of copper is 8.9 gram per centimeter cube and its RD is 8.9.
Difference between density and relative density. Despite of the relation between the density and relative density, as we saw in the previous slide, there are also some differences between them. There are three major points of differences. Number one, definition. Density is defined as mass per unit volume of the substance, whereas relative density is defined as the ratio of the density of the substance to the density of water at 4 degrees Celsius. Number two, value in measurement system. The value of density is different in different systems of measurement such as SI system or CGS system, whereas in the case of relative density, there is no such difference in the value. Number 3. Unit. The units of density are gram per centimeter cube and kilogram per meter cube, whereas relative density has no such units. On relative density. The question is, a globe has a mass 12 grams and a volume.
Swana, unmute yourself.
Find its relative density. According to the solution, relative density equals to mass of.
Anuja, the sound is coming low. Can you just increase the volume of this sound? Unmute your. Yes, Atre. Yes, start. Okay, continue.
The question is, a globe of steel has a mass of 12 gram and a volume of 15.2 centimeter cube. Find its relative density. According to the solution, we know relative density equals to mass of any volume of a substance by mass of an equal volume of. And the question, it is given that the mass of the globe is 12 gram and its volume is 15.2 centimeter cube.
Now, the mass of 50 centimeter cube of water is 1 gram per centimeter cube in 0.0 centimeter, which is equals to 50 gram. Therefore, the relative density equals to 12 gram by 15.2 gram. That is equals to 0.79.
Instruments used for measuring the relative density of a substance. The hydrometer is an instrument which is used for measuring the relative density of liquids. And the instrument which is used for measuring the relative density of milk is called the lactometer. It is used for testing the purity of milk by measuring its density. So by this, we come to an end of our presentation. Thank you everyone for your cooperation and interest.
Very good presentation, children. So we move to the next team. Can you just put your hands down so that I can make the next team the presenter? So we move on to we have finished off relative density. Fifth team, flotation. Fifth team, flotation.
Am I audible, ma'am?
Yes, yes. Just
Okay, ma'am, I am presenting my slide.
yes, just raise your hand so that I can make you all the presenter. Otherwise, you all won't be able to present because you all are attendees. Okay. So last team, get ready, children. And remember, children, try to stick to the time span. Okay, from next time, try to see that if it is a 10-minute slot, should not be more than 10 minutes. Okay, you should have know how to uh, compress it within that time schedule. So
Ma'am, I
first,
can't find the settings in my computer. Raise hand.
okay, I've made you the presenter, Sneha.
Okay, ma'am, thank you.
Now start presenting. The last team, get ready, children.
Morning. Today, Team Slide Group would like to present to you a short presentation on the concept of flotation. When a body is in a fluid, two forces act on the body, which are as follows. Number one, a force equal to its weight acting vertically downwards. Number two, a buoyant force or an upthrust acting vertically upwards. Now, according to the principle of flotation, the weight of the floating body is equal to the weight of the liquid displaced by its submerged part. That is, weight of the floating body equals to weight of the fluid displaced is equal to buoyant force. Now, the apparent weight of a floating body is zero, thus a floating body always appears to be weightless. Following are the cases we find when an object is placed in a liquid depending upon the maximum upthrust, whether it's less than or equal to or greater than that of the weight. Case 1. When the weight of the object is greater than that of the buoyant force, that is, in such a condition, the object will sink. The apparent weight of the body will be weight minus upthrust. The density of the object is greater than that of the density of the liquid. Case 2. When the weight of the object is equal to the upthrust, that is, in such a condition, the object will float just below the surface of the liquid. The apparent weight of the body will be zero. The density of the object is equal to the density of the liquid. Case 3. When the weight of the object is less than that of the upthrust, that is, in such a condition, the body floats partially inside the liquid and complete immersion. The apparent weight of the body is upthrust minus weight, and the density of the liquid is greater than that of the density of the solid. Laws of flotation. A body floats in liquid if the density of material of the body is less than or equal to density of liquid. If density of material of the body is equal to density of liquid, the body floats fully submerged in liquid in neutral equilibrium. When body floats in neutral equilibrium, the weight of the body is equal to weight of displaced liquid. The center of gravity of the body and center of gravity of displaced liquid should be in one vertical line. Seeing the relation between volume of submerged part of a floating body, the densities of liquid and the body. Let us consider capital B be the volume of a body of density capital B. Let the body be floating with its volume small v immersed inside the liquid of density small v. Then the weight of the body W is equals to volume multiplied by the density of the body multiplied by acceleration due to gravity. That is equals to capital V, capital D, G. Weight of the liquid displaced by the body at first F is equals to the volume of the displaced liquid multiplied by the density of the liquid multiplied by acceleration due to gravity. That is equals to small d, G. For flotation, the weight of the body should be equals to the upthrust, that is capital V, capital D, G equal to small d, G. And by cancelling out gravity on both the sides, we get small v by capital V is equals to capital D by small d. Hence, we can say that the ratio of the volume of the submerged part to that of the total volume of the body is equal to the ratio of the density of the body to that of the liquid. And now, a floating body of higher density has its more volume submerged inside the liquid and hence experiences higher upthrust than the body of low density. A body floats in liquids of different densities only and only when the density of the body is less than or equal to the density of the liquid. The volume of the body submerged in the liquid will decrease with the increase in the density of the. Why icebergs are dangerous for sea? Density of seawater is 1.026 grams per centimeter cube and the density of ice is 0.917 grams centimeter cube approx. The density of seawater is more than the density of ice, hence icebergs float in seawater. The weight of seawater displaced by almost 19 of the total volume of the iceberg that remains submerged under seawater. Balances the total weight of the iceberg and thus it floats in water with only 1/10 portion of its total volume visible above the surface of seawater. A ship may collide with the invisible submerged portion of the iceberg being completely unaware of its presence and unable to estimate the size and shape of the iceberg present underwater. Hence, icebergs are dangerous for ships. There is no change in level of water on melting a floating piece of ice. When a floating piece of ice melts into water, it contracts by the volume equal to the volume of ice piece above the water surface while floating on it. Hence, the level of water does not change when the ice floating on it melts. The balloon does not rise indefinitely. The reason is that the density of air decreases with altitude. Therefore, as the balloon gradually goes up, the weight of the displaced air, that is, upthrust, decreases. It keeps on rising as long as the upthrust on it exceeds its weight. When upthrust becomes equal to its weight, it stops rising further. Since the iron ball sinks and the ship keeps floating, this is because the density of water is 1 gram per centimeter cube at 4 degrees Celsius, while the density of iron is 7.8 gram per centimeter cube. As density of iron is greater than density of water, and the same iron ball sinks in water. The ship made of iron, on the other hand, is hollow from the inside and contains air. Thus, the average density of the ship is less than the density of water, and so the iron should float from water with the portion submerged inside water. While floating, the weight of the ship is balanced by the weight of the water displaced by the submerged portion of the ship. Hence, its floats. In case of solid iron ball, weight is greater than upthrust. Hence, it sinks. The submarine float or sink in water as and when desired. A submarine is a streamlined watertight boat capable of underwater movement and is provided with ballast or flotation tanks in the front and rear parts. To make the submarine dive in water, its ballast tanks are filled with seawater, so that the average density of the submarine becomes greater than the density of seawater and thus it sinks. Now, to make the submarine rise to the surface of seawater, water from the ballast tanks is forced out into the sea by allowing compressed air to enter into the ballast tanks. This makes the average density of the submarine less than that of seawater and thus it rises up. When floating in water, the weight of the water displaced by the small submerged portion of the submarine balances the total weight of the submarine. Now, the plimsoll line. We all know a ship has a white line painted on a sign known as a principal line. Now, this line indicates the safe limit for loading the ship in water of density 10 to the power 3 kg per meter cube. A ship is not allowed to be loaded further when its plimsoll line starts touching the water level, so that when it sails in seawater of density more than 10 to the power 3 kg per meter cube, only the part of it below the plimsoll line remains submerged in water.
Now, why it is easier for a person to swim in seawater than in river water? Seawater contains dissolved salts and minerals, and the average density of the seawater is more than that of the river water. And according to the law of flotation, upthrust on a person is due to the submerged part of the body, that is the weight of the body. As the weight of the body remains same, so the upthrust acting is same for both the cases. The density of seawater is greater than the density of the river water. Therefore, the volume submerged in sea river water is greater than that of the volume submerged in seawater. Hence, the person in seawater floats with relatively lesser portion submerged in seawater, while in river water, a greater portion of body is submerged underwater. Thus, it is easier for a person to swim in seawater than in river water.
Here are some interesting facts first on the concept of flotation. Do you know pumice is the only rock that floats on water? The reason is because of the pockets of gases in its pores, but still it's unknown how it floats for such a long period. We all know that ice cube floats in normal water, but have you ever heard that heavy water ice doesn't float, it sinks in normal water, but that too float when kept in heavy water? Now, what is a heavy water? It is actually made from deuterium and hydrogen isotope. Do you know floating has a lot of health benefits? It helps us to combat from anxiety, depression, improve sleeps by minimizing our cortisol production. Do you know an orange floats on water whereas a peeled orange doesn't float? The reason behind is an orange contains spores which traps air which makes its average density less than that of water. Do you know the salt concentration of the Dead Sea fluctuates around 31.5%? This is usually high and anyone can float in the Dead Sea because of its natural buoyancy. We would like to express our special thanks of gratitude to our teacher, Anisha ma'am, who gave us the golden opportunity to create this wonderful presentation during the static lockdown. And lastly, I, being the group leader, would like to thank all my group members for their consistent support and wonderful coordination.
Excellent, children, excellent. I'd like to include some of your points in my lecture too. Very nice. That peeled orange part was really nice. It did not come in my mind. Very good, very good. Now we move on to the last team. Put your hands down, children. Um, Last team, children, we rely on you all to give us the total conclusion of the chapter. Then we would request Amitav sir to inspire you all and we will end the meeting. So after your lecture, sir will tell us, give us inspiration, how we can move forward for better results, for better improvement in your later life. This is not the end. You're just in class 9, long, long way to go. And sir, I've seen many, many children being succeeding in their life, and he knows he's more experienced. He will help you out for your future life. So, last team, I want to make you the presenter. So, can you just raise your hand? You're going to give us the full summary of today's PowerPoint presentation, the full chapter as a whole. So Biash is going to present. Biash, get ready with your team. I'm making you all the presenter. Anyone else who is not met the presenter, just let me know. So after this, we would request Amitav sir to give us a few tips of how we can proceed. Then I will forward the recording to Amitav sir and Reshmi so that they can have another look to your presentation and they will declare by next week you will get your results. Okay, so get ready, children. We are going to have the full summary of the chapter upthrust, relative density, and flotation.
Ma'am, is my screen visible?
Yes, yes, it's visible.
Good morning to our respected ma'am and honorable judge. Team Newton would like to present to you a short presentation on upthrust in fluids, Archimedes' principle, and flotation. Starting with our first topic, upthrust.
Upthrust, an object that is partly completely submerged, experiences a greater presence pressure on its bottom surface than on its top surface. This force is called upthrust. Its SI unit is Newton. Formula: upthrust F equals to volume of the body submerged in liquid into density of the liquid into acceleration due to gravity. Now we will move on to the some characteristics. Number 1. Larger the volume of body submerged in fluid, greater is the upthrust. Example, like the feel lighter in swimming pool or water. This is due to this reason because the effect of upthrust is that weight of the body immersed in a liquid appears to be less than the actual weight. Second characteristic, more the density of fluid, greater is the upthrust. For some volume inside the fluid, greater is the upthrust. Example, volume of a block wood immersed in a glycerine is smaller as compared to the volume of block immersed in water because density of glycerine is more than that of water. Hence, glycerine exerts more upthrust on the block of wood than water, causing it to float in glycerine with a smaller volume. And the last characteristic is that the upthrust acts on the body in upward direction at the center of gravity of the displaced fluid, which is called the buoyancy. It explains that upthrust is caused due to the upward force which is exerted by a liquid on the body which is immersed in it. As it this force that the heavy object seems to be lighter when immersed in water. When an object is immersed in a liquid, buoyant force acts in all directions. Thank you.
Archimedes' principle. Archimedes' principle states that the upward buoyant force that is exerted on a body immersed in a fluid, whether partially or fully submerged, is equal to the weight of the fluid that the body displaces and acts in the upward direction at the center of mass of the displaced fluid. Example: a ship floats on water due to Archimedes' principle. Thank you.
Experimental verification of Archimedes' principle. Take a solid, suspend it by a thin thread from the hook of a spring balance, note its weight. Now take a Eureka can and fill it with water to its spout. Arrange a measuring cylinder below the spout of the Eureka can. Now immerse the solid gently into the water of the Eureka can. The water displaced by it gets collected in the measuring cylinder. When the water stops dripping through the spout, note the weight of the solid and the volume of the water collected in the measuring cylinder. Since the density of its water is 1 gram, the volume of water collected in the measuring cylinder is equal to the mass of the water is displaced.
Relative density of a substance is also defined as the ratio of the mass of a certain volume of a substance to the mass of an equal volume of water at 4 degrees Celsius. It is a scalar quantity, and since it is a ratio, it is a unitless property. The difference between density and relative density. Density of a substance is the mass per unit volume of that substance, whereas the relative density of a substance is a ratio of density of that substance to the density of water at 4 degrees Celsius. Density is expressed in gram per centimeter cube or kg per meter cube, whereas relative density is a unitless property. Now we move on to the next slide.
Determination of relative density of solid. To determine a relative density of solid, we conduct a following experiment. Suspend a given solid with a thread from the hook of the left pan of a physical balance and find its weight. Now, place a wooden bridge over the left pan of the balance and place a beaker nearly 2/3 filled with water on the bridge. Immerse the solid completely in water such that it does not touch the walls and bottoms of the solid in water. We observe that the weight of the solid in water equals to W1GF and the weight of the solid in water equals to W2GF. Hence, the calculations are loss in water of the solid when immersed in water is W2 minus W1GF. Therefore, the relative density of solid is W1 by W2 minus W1. Hence, we move on to the next slide. Relative density of liquid. To find the relative density of a liquid, we take a body which is heavier than both the given liquid and water and also insoluble in both. The body is first weighed in air, then in liquid, and then after washing it with water and drying, it is weighed in water. If the weight of the body in air is W1GF, in liquid is W2GF, and in water is W3GF, then from the above equation, we can find the relative density of liquid, which is W1 minus W2 by W1 minus W3. A hydrometer is an instrument which is used for measuring the relative density of a liquid directly and hence to test the purity of a liquid. We move on to the next topic, flotation.
Flotation. Laws of flotation. A body floats in a liquid if density of the material of the body is less than or equal to the density of the liquid. Point 2. If density of material of a body is equal to density of liquid, the body floats fully submerged in liquid in neutral equilibrium. Point 3. When body floats in neutral equilibrium, the weight of the body is equal to the weight of the displaced liquid. Point 4. The center of gravity of the body and center of gravity of the displaced liquid should be in one vertical line. The application of flotations are to control the applications of flotation we would like to explain with this example of submarine. To control its buoyancy, the submarine has ballast tanks and auxiliary or trim tanks that can be alternately filled with water or air. See animation below. When the submarine is on the surface, the ballast tanks are filled with air and the submarine's overall density is less than that of the surrounding water. As the submarine dives, the ballast tanks are flooded with water and the air in the ballast tanks is vented from the submarine until its overall density is greater than the surrounding water and the submarine begins to sink. A supply of compressed air is maintained aboard the submarine in air flasks for life support and for use with the ballast tanks. In addition, the submarine has movable sets of shock wings called hydroplanes on the stern that help to control the angle of the dive. The hydroplanes are angled so that the water moves over the stern, which forces the stern upward. Therefore, the submarine is angled downward. Another application of principle of flotation is an iron nail sinks in water while a ship floats. Now, if we try to place an iron nail on the surface of water, it will sink. This is because the density of iron is greater than that of water. So the weight of the nail is more than the upthrust of water on it. On the other hand, ships are made of iron, but they do not sink. This is because the ship is hollow and the empty space in it contains air, which makes its volume large and average density less than that of water. Therefore, even with small portion of ship submerged in water, the weight of the portion of the weight of the water displaced by the submerged part of the ship becomes equal to the total weight of the ship and therefore it floats. We would like to go to the next.
The apparent weight. The apparent weight is a property of objects that corresponds to how heavy an object is. As you can see in the slide, the apparent weight of an object will differ from the weight of an object whenever the force of gravity acting on the object is not balanced by an equal but opposite normal force. Now you can ask me what is the difference between apparent weight and true weight. Actually, true weight is the product of mass and gravitational acceleration, which is equal to mg, or mass into gravitational acceleration. And in the other hand, apparent weight is the sum of net forces. Therefore, in other words, the apparent weight of an object will differ from the weight of an object whenever the force of gravity acting on the object is not balanced by an equal but opposite normal force. That's it. Thank you.
We come to the end of our short presentation. Thank you.
Excellent, children. So we have learned very good presentation by all of you. Although y'all did not get together, children. Although y'all did not get together, just at the tender age of class 9 to do something what children do in college. It's really wonderful for you. Okay. Now we are going to request Amitabh sir. Sir, we are waiting for you to tell us a few words.
Good morning, ma'am.
Morning, sir. So the children
Good
have
morning.
tried their best, sir.
Okay, ma'am. Good morning, students.
Good morning, sir.
Good morning, sir.
Good morning,
Morning,
sir.
sir.
Good morning, sir.
Good
Good
morning,
morning.
sir.
Very good morning.
Good morning,
Good
sir.
morning.
Good morning, sir.
Good morning, sir.
Sir. Okay, good morning. First, I want to thank Anessa ma'am that she honored me as a judge of the competition. Also, I congratulate to all of you. Okay, all of you have done very well. It's good performance, good presentations. Okay, you must remember that this in this first world, nobody has enough time. So this type of presentation should be compact, and maximum number of information or points should be presented in short duration. Okay. This type of competition will help you to improve your thinking power, your imagination, and also help you to appear for an interview in your professional life. In future, it will help a lot. It's my advice to all of you that don't try to learn blindly to get marks in the exam, but try to understand the subject, love that subject, whatever may be the subject, is maybe physics, chemistry, maths, everything. Marks will come automatically. Always try to remember key points of the topic. Now all of you are read physics books, which contains only 100 to 120 pages only. But in future, its volume will be more. Now we are studying the chapters like light, sound, electricity, etc. In future, every chapter will be a separate book of 300 or more pages. Okay, so how much will you learn blindly? Try to understand that subject. For your school exam or your ICSE board exam, read the textbook properly and mark the keywords so that at the time of exam, you can revise it in a very short time. Because at that moment, you will not get more time. So today, out of 6 teams, 3 teams will be declared as first, second, and third. So it does not mean that other groups couldn't perform well. This time, these 3 groups have done better. But next time, other groups can perform better than these groups. So remove the word failure from your mind or dictionary. Always think positive. This time we couldn't, but next time we will be the best. At the end of my speech, I want to say all of you that all of you are very lucky that you got a physics teacher like Annesha ma'am. She is not only a good teacher, but also a good human being. Her motherly nature towards her students impresses me a lot. A lot of good students have passed out with good results under ma'am's guidance. So if you have any problem, you ask ma'am, she will help you. Okay, thank you. Thank you, ma'am.
Thank you, sir. Thank you, Reshmi children. And listen, children, just to repeat what sir said. Children, now you are learning a few pages. Just as you move out, sound will become a book. Light will become a book. Okay, electricity will become a big book. So how much you will learn? Thing is, you have to get this all the subjects inside. You have to get all the subjects inside. And next time, after all our exams are over, we'll again enter into a PowerPoint presentation. There, as sir said, you have to make your things compressed. Okay. Now, congratulations to all of you, all of you. So, with sir, with your permission, we are ending the meeting today. Yes, sir. So I'm taking your
Okay,
kind
ma'am.
permission and ending the team. I'll send you the recording.
Okay, ma'am. Thank you.
Thank you, sir. Thank you, Reshmi. Thank you.
Okay. Bye bye, students.
Bye, sir. Thank you, sir.
Bye, sir.
Bye.
Thank you,
Bye.
sir.
Bye. Okay.